So welcome to our second lecture on the VSEPR shape of molecules. In the first lecture, we were talking about how when atoms use all their valence electrons to form bonds, those resulting bonding pairs of electrons are trying to get as far apart from each other as they can. And as a result, they drag the atoms they're associated with into different positions. And so depending on how many bonding pairs of electrons you have around the central atom, you get different shapes of molecules. So for the simple 2 electron pairs, we get a simple linear shape. For 3 pairs of electrons, we get the trigonal planar arrangement. For the 4 pairs of electrons, we get the tetrahedral shape. The problem we ran into with shapes, however, was when we talked about the water molecule. The water molecule has 2 bonding pairs of electrons holding the 2 hydrogens to the oxygen. But those bonds don't end up being 180 degrees apart. VSEPR says they should get as far apart as possible, but they end up not at 180 but about 105 degrees. And the question was, why would they not end up at 180? And the point is, VSEPR is a valence shell electron pairs, repulsions. The oxygen starts out with 6 valence electrons. It only uses 2 of them in bonding, which means it also has 2 lone pairs. The result is that in the water molecules, we don't have just 2 bonding pairs of electrons trying to get away from each other. We actually have 4 pairs of electrons trying to get away from each other. And so the 2 bonding pairs do not end up 180 degrees apart. Instead, they're trying to get away from the other 2 lone pairs as well as the other bonding pair. And so they do not end up 180 degrees. They go into a bent arrangement. And this is something important that we have to keep in mind. When we're talking about shape, we're not talking about where the electrons are. The electrons might decide where everything is ending up. The electrons themselves are invisible. We never get to see the electrons themselves. Instead, when we look at atoms and molecules, what we see are the slow, dumpy parts, which in the atom is basically the nucleus. So when we look at atoms and molecules, what we are actually seeing is where the atoms are. And so when we talk about shape, we're talking about the arrangement of the atoms in the molecules, not the arrangement of the electrons. The electrons might be deciding where everything is ending up, but they are not the shape of the molecule. The shape of the molecule is where the atoms are coming from. If we look at a molecule like tin dichloride, the tin starts with 4 valence electrons. The chlorines each start with 7. So each of the chlorines puts in 1 electron, and the tin puts in 1 electron. And then the second chlorine puts an electron in, and the tin puts in its second electron. And we get 2 bonding pairs of electrons. But the tin still has 2 valence electrons, and they end up as a lone pair. And so we end up with 3 pairs of electrons around the tin. 2 bonding pairs and 2 non-bonding pairs. And so what is our shape going to be? Well, the 3 pairs of electrons are going to go into a trigonal planar arrangement, because we said that's the arrangement 3 pairs of electrons go into, but that's not the shape we're going to get for the molecule. In the tin dichloride, the electrons end up in their trigonal planar arrangement. But since the lone pair has nothing hanging off of it, it becomes invisible. And we are only left with that shape, which is bent, and that angle is about 120 degrees, not 180. The shape of the electrons is trigonal planar, but the shape of the molecule is bent. We can look at ammonia. In ammonia, the nitrogen starts with 5 valence electrons, uses 3 of them in bonding to each of the 3 one each to each of the 3 hydrogens, and that leaves it a lone pair. So again, we have 4 pairs of electrons around the nitrogen, but only 3 of them are bonding, 1 pair is non-bonding. Well, the 4 pairs of electrons go into a tetrahedron. We said that's the arrangement 4 pairs of electrons want to go into. But that's not the shape of the molecule, because there isn't anything hanging on the lone pair, and therefore we only see the 3 hydrogens and the nitrogen when we're talking about the shape. In the ammonia molecule, the 4 pairs of electrons again go into our tetrahedron. But in this case, there's again nothing hanging on the lone pair. So we are ending up with that shape instead. Again, it's triangular, but now it's not planar. All 3 of the hydrogens are below where the nitrogen is. So it's not trigonal planar, that's a trigonal pyramid arrangement around the nitrogen. Which brings us back to the water molecule we looked at before. The water molecule, the oxygen starts with 6 valence electrons, uses 2 in bonding to the 2 hydrogens, and so it is left with 2 lone pairs that are also in its valence shell. So again we have 4 pairs of electrons, but this time 2 of them are bonding and 2 of them are not bonding. Well, once again, the non-bonding pairs become invisible, and we only see where the 2 hydrogens and the oxygen are, which give us a bent shape. Finally, we come back to the water molecule. The water molecule, of course, has 4 pairs of electrons around the oxygen. But in this case, 2 of them are invisible because there's nothing hanging on them. And we are left with only the 2 bonding pairs with their hydrogens on them to see. And again, the electrons are in a tetrahedron. But the molecule's shape is again bent, because it's only the atoms that we can actually see, not the electrons. You have to remember, we said a covalent bond was a pair of electrons shared between 2 atoms. And the thing you have to realize is that between is not figurative, it is literal. The pair of electrons has to actually be in between the 2 nuclei that it's holding together. It can't be anywhere else. The only reason the nuclei are willing to be that close together is because the 2 electrons are in between them. And so, the bonding pairs of electrons are stuck. There's one place they absolutely have to be. They have to be between the 2 atoms they're holding together. Meanwhile, the lone pairs don't have to be any place in particular. They just got to be somewhere around the atom, and as a result, they're sort of just hanging out. And the result is they also spread out. Since they are not as confined as the bonding pairs are, they tend to take up more space. And so what we see happen in the water molecule is the 2 bonding pairs of electrons get squashed a little bit closer together by the lone pairs, and so the angle ends up being 105 degrees rather than 109 degrees. So we see the shapes of the molecules doesn't depend on only the bonding pairs of electrons. It depends on where all the electrons are around the central atom. If we have 2 bonding pairs, and that is all there is around the central atom, we get a linear shape. If we have 3 pairs of electrons, 3 pairs of electrons want to go into a trigonal planar arrangement. And if all 3 of the bonding pairs are there, then we do in fact get a trigonal planar molecule. But if only 2 of the electron pairs are bonding, if there's a non-bonding pair, the electrons are in a trigonal planar arrangement, but the molecule ends up being bent in shape because we see only where the atoms are. And that bond angle would be about 120 degrees. If we have 4 pairs of electrons, 4 pairs of electrons want to go into a tetrahedron. If all 4 of the pairs are bonding, then we do in fact get a tetrahedral shape for the molecule. But if only 3 of the pairs are bonding and there's a lone pair, then we don't get a tetrahedron. Instead, we get a trigonal pyramid shape. The atoms of the bonded pairs all end up below the central atom. And finally, of course, if you have 2 bonding pairs and 2 non-bonding pairs, the electrons are in a tetrahedron, but we only see the 2 that are in the bonding position, and again we end up with a bent molecule now where the angle is going to be about 109 degrees instead. That concludes our second lecture on using VSEPR to get the shapes of molecules. Have a nice day.